Welcome to the Discrete Universe podcast. Today, we're really diving into something core about quantum geometry dynamics, QGD, something that really sets it apart, especially for you folks listening who have a background in fundamental physics.
Right.
We're going to unpack why QGD, in its axiomatic setup, it just doesn't use concepts like groups or gauge theory.
Yeah, which are, absolutely central to the standard model and, well, most quantum field theories, really.
Exactly. So what's going on? What are the foundational ideas in QGD that lead it down this very different road?
It's a great question. And it's not just like a different mathematical trick. The reason QGD avoids these tools, these incredibly powerful tools, actually stems directly from its fundamental assumptions about reality itself.
Okay.
So maybe the best way is to quickly lay out the pillars QGD is built on, focusing on why they point away from groups and gauges.
Yeah, let's do that. Hit us with those foundational principles. What makes QGD tick differently?
Okay, so first, maybe most importantly, is strict causality. The idea is that every state, every single configuration of the universe is strictly and uniquely caused by the state immediately before it.
Like a perfect chain reaction? No wiggle room?
Exactly. Completely deterministic at the most fundamental level. Second, fundamentality itself is defined by invariance, meaning the truly fundamental things, the basic building blocks and their properties, they don't change, ever. They're conserved constants for the entire life of the universe.
Okay, so no evolving fundamental constants or anything like that in this picture.
Correct. And these fundamental entities, QGD proposes just two.
Mm-hmm.
Preons plus
They're trions.
fermions.
Yes.
They're eternal, and the total number of each type is fixed and finite. Crucially, though, and this is a big one, QGD says that space itself, quantum geometrical space, is fundamentally discrete.
Not continuous, like pixels instead of a smooth picture.
That's a good analogy. It's granular at the bottom level. This is a major break from the continuous space-time manifold that, underlies general relativity and standard quantum field theory.
Huge break. Okay, what else?
And finally, matter, everything we see emerges when these preons bind together. There's an attractive force between them called p-gravity that does this.
P-gravity? Okay.
So these axioms together, strict causality, invariance, finite preons, discrete space, and p-gravity, they just paint a very, very different starting picture compared to theories built on continua and symmetries from the get-go.
Right, so you've got this foundation, discrete, causal, invariant, built on these preons. How does that explicitly lead to rejecting continuous space-time? And, why does that mean you might not need things like gauge symmetries?
Well, the fundamental discreteness of space is really key here. QGD argues that the smooth, continuous space we experience is just an emergent property at our scale.
Like the smoothness of water emerging from discrete molecules.
Precisely. But if space isn't infinitely divisible at the fundamental level, then a lot of the mathematical machinery built on that assumption, like calculus on manifolds in the usual sense, might not be the fundamental language. It challenges the applicability of infinities.
Okay, I see that for space. But what about time? Time is woven into space-time and field theories, crucial for dynamics.
QGD takes quite a radical stance on time, too. It suggests time isn't actually a physical dimension or entity in the same way space might be considered geometrically.
So what is it then?
It's more like a mathematical parameter, a way we track the sequence of these discrete, causally linked states. Think of it as counting the steps in that deterministic chain reaction.
So physical properties like mass, energy, momentum, they don't depend intrinsically on time.
Exactly. They're defined by the state itself, the configuration of preons, independent of this external time parameter. This view even challenges the idea of a purely mathematical continuum, like the number line, arguing that even mathematical operations need physical processes which cost finite energy. So the concept of actual infinities is questioned.
Wow, okay. That's a lot to chew on. So if you don't have this fundamental continuous space-time, and time is just a parameter, how do you recover the physics we observe, especially forces? How do they work without the standard gauge boson picture?
Right, that's the critical step. QGD's goal is to derive all observed physics directly from the properties of the preons and their interactions within this discrete quantum geometrical space.
Derived, not postulated through symmetry.
Exactly. So take electromagnetism, for example. Instead of arising from a fundamental U1 gauge symmetry mediated by photons,
Yeah.
QGD proposes it emerges from how the underlying preonic field gets polarized or distorted by the presence of charged particles, which themselves are just specific arrangements of preons.
So the force isn't mediated by exchanging a fundamental particle tied to a symmetry. It's more like a a stress or strain in the underlying preonic fabric.
That's a very good way to put it, a collective effect of the substrate. Even something as fundamental as the speed of light isn't just put in by hand.
How does that work?
It's proposed to be a direct consequence of the fundamental speed at which the prions, plus themselves, move or propagate changes through the network.
Huh. Derived.
Derived. And things like the weak equivalence principle or gravitational redshift and light bending phenomena, usually explained by GR's geometry, QGD, derives them from its own gravity equation. And interestingly, that equation implies gravity acts instantaneously.
Instantaneously. Okay, that's another major departure.
It is. But the point is, these phenomena are meant to emerge from the discrete causal dynamics, potentially making fundamental gauge symmetries, as we usually think of them, unnecessary building blocks.
It definitely sounds like QGD is pushing for a very minimalist approach. Trying to explain the maximum amount of physics with the minimum number of fundamental ingredients and rules. Is that driven by a specific philosophy, like Occam's razor?
Absolutely. It strongly embraces a form of Occam's razor, but specifically what philosophers might call qualitative parsimony.
Meaning fewer types of things.
Exactly.
Yeah.
Minimize the number of kinds of fundamental entities, just the two prions and fundamental principles, just strict causality and invariance. The aim is to build complexity from that simple base, rather than starting with a more complex set of symmetries or fields. It's about avoiding what QGD considers unnecessary assumptions about the fundamental layer.
Okay, so we're building physics from the ground up. Prions, discrete space, strict causality. Let's really pin down now why this specific framework leads QGD away from group theory and gauge theory. Because for anyone familiar with, say, the standard model, its elegance and predictive power are so tied to those mathematical structures. This is a big hurdle conceptually.
It is. And group theory and gauge theory are undeniably incredibly successful. They provide the mathematical language for symmetries, which, in the standard model, dictate the fundamental forces through gauge bosons. It's a beautiful picture.
Right.
But if QGD's foundational picture is correct, if space is discrete, if the only fundamental things are prions with fixed properties, and if interactions are strictly causal propagation through this prionic network, then the need for continuous symmetries and their associated gauge fields as fundamental ingredients might just dissolve.
They might become emergent properties themselves,
Yeah,
or just not the right description at the bottom level.
potentially both. The symmetries we observe in models so well with group theory might be approximate descriptions that emerge at larger scales, kind of like fluid dynamics emerging from particle interactions.
Yeah.
Or the fundamental mechanism of interaction in QGD is just intrinsically different and doesn't map onto a gauge principle.
Can we contrast it again, maybe with another force like gravity?
Sure. So in theories aiming to quantize gravity within a continuum, you often look for something like a gauge theory for space-time symmetries, leading to the idea of a spin-2 graviton mediating the force.
Right.
In QGD, gravity isn't mediated by a particle traveling through space-time. It's described as an instantaneous change in the state of the entire prionic network due to the presence and distribution of mass, which itself is just a property related to configurations of prions. It's a global, instantaneous adjustment of the network's tension, if you will.
So again, an effect of the substrate, not a messenger particle tied to a symmetry.
Yeah, exactly. The forces aren't fundamental entities tied to mathematical symmetries. They're consequences, emergent phenomena arising from the dynamics of the truly fundamental stuff, the prions and their discrete space.
QGD seems to be saying, let's start with the simplest possible discrete constituents and rules and see if the complexity, including apparent symmetries, emerges naturally rather than starting with the symmetries.
That's a perfect summary of the philosophical approach. Build complexity from the bottom up without imposing higher-level structures, like continuous symmetries at the foundational level.
Okay, this is definitely a paradigm shift in thinking. If it's so different, it must make some very specific, testable predictions that could distinguish it from theories like the standard model or extensions that rely heavily on gauge symmetries.
Absolutely, and that's crucial,
Yeah.
right? A different framework needs to offer different falsifiable predictions. QGD does make several quite unique ones.
Such as?
Well, for one, it predicts a specific structure for what we currently interpret as dark matter halos around galaxies. It suggests the density profile should be different from the cuspy profile, often predicted by standard cold dark matter models. QGD predicts something more related to the prionic field polarization.
Interesting. Anything else on galactic scales?
Yes, it also predicts that galaxy rotation curves should remain flat, essentially indefinitely, far out from the center, purely due to the galaxy's own mass distribution polarizing the prionic field, without needing external influences or modifications to gravity itself at those scales.
Okay, different dark matter profile, flat rotation curves built in. How about phenomena explained by force carriers, like the LIGO-Virgo signals?
That's a big one. QGD interprets the signals detected by LIGO and Virgo not as gravitational waves, ripples in continuous spacetime predicted by GR, but as preonic waves.
Preonic wave?
Yeah, essentially fluctuations in the polarization state of this underlying preonic field propagating through the network. Now, distinguishing these experimentally from standard gravitational waves would require finding unique signatures predicted by QGD, which is obviously a major challenge.
A huge challenge, I imagine. Are there other, maybe more accessible tests?
There are some potentially more direct ones. QGD predicts, for example, subtle but quantitative differences in the electromagnetic interaction strength depending on the type of interacting particles.
How so?
Like the electromagnetic force between an electron and a proton might be slightly different from that between a muon and a proton beyond known QED effects. This arises because electrons and muons in QGD are different configurations of preons and thus polarize the preonic medium slightly differently. That's something potentially measurable in high-precision experiments.
That is specific. Any other really unusual predictions?
Well, it offers explanations for cosmological observations, like the universe's accelerating expansion, without needing a separate dark energy component. It attributes these large-scale effects to the overall structure and polarization dynamics of the universal preonic field.
So dark energy is also an emergent effect of the preonic substrate.
That's the idea. And perhaps the most, well, startling prediction is that nuclear decay events here on Earth could potentially be triggered or influenced by powerful gravitational events happening far across the universe via these instantaneous changes in the preonic network.
Triggering nuclear decay remotely.
Yes. The idea is that a massive disturbance, like a supernova or merger, instantly adjusts the tension of the preonic network everywhere, and that tiny change could be enough to tip an unstable nucleus over the edge. QGD envisions testing this with what it calls gravitational telescopes, essentially networks of decay detectors.
That's definitely unconventional. Okay, so summing up, the reason QGD doesn't employ groups in gauge theory isn't because it missed them or thinks they're unimportant for describing current physics.
Not at all.
It's because its fundamental building blocks, discrete space, fundamental preons, strict causality, lead to a picture where forces and phenomena emerge differently, potentially without needing those continuous symmetries as fundamental postulates.
It's a quest for a different kind of simplicity.
Precisely. It's simplicity in the initial assumptions, in the ontology. The hope is that the observed complexity, including the apparent symmetries we model with groups, arises naturally from that minimal foundation. This deep dive really shows it's a fascinating alternative way to think about fundamental reality. It certainly throws established concepts into a new light, doesn't it? Makes you really question the assumptions behind phrases like continuous space-time or fundamental symmetry. What is the true nature of space? Is time fundamental? How do forces really work at the bottom?
Exactly. And it makes you wonder, what other implications might this kind of discrete causal framework have that haven't even been fully explored yet? It challenges us physicists to keep an open mind.
And it challenges you, our listeners, especially those with that physics background, to consider which parts of this QGD picture seem most compelling. Where do you see the biggest conceptual or experimental hurdles? These are the kinds of questions that push the boundaries of physics.
Indeed. It's all about exploring different paths to potentially reach a deeper understanding.
Well, thank you for joining us on this deep dive. We hope this exploration into quantum geometry dynamics, and specifically why it takes a different path regarding groups and gauge theory, has given you some thought-provoking ideas to consider. We definitely encourage you to look into the source material if your curiosity is piqued.
Thanks for listening.